This is a recording for Chapter 7. We'll be talking about the one-way analysis of variance, which is a parametric version, and the non-parametric version, which is Kruskal-Wallis H-test. So essentially what these analyses do are more or less extensions of the t-test. What we're going to be looking at when you utilize these types of analysis is that you're looking at least 3 more groups. Remember, if you recall the t-test looked at the differences between 2 or more groups, and then when you factor in 3 or more, then you would move from the t-test to the analysis of variance if you're looking at the mean differences. If the statistical assumptions of normality, etc., aren't met, then you might look at the median differences, and then you would move to that non-parametric version. Okay, so if you have an example research question, such as you're looking at comparing the length of stay. The length of stay is an outcome variable between 3 different hospitals, so you have at least 3 different groups. You could look at that using an ANOVA, or comparing birth weight being the outcome among different ethnic groups, and you can have many more than just 3 variations of ethnic groups that you could be looking at the differences between. Our grouping variable, remember our grouping variable isn't necessarily our independent variable. In statistics terms, the grouping variable is usually indicated as a factor, so that this grouping variable will parse out the information into at least 3 more groups, and like it says here, it's often not the independent variable. If we go back to our example of looking at birth weight by ethnicity, we have 3 grouping variables here. We have African American, Caucasian, and Hispanic. The characteristic of interest, which is otherwise known as the outcome or dependent variable, needs to be at least an interval ratio or ordinal. It's classified as a dependent variable, or you could call it the outcome variable. Things like length of stay, cost of care, self-rated pain scale, etc. So these are our outcome variables. Getting back to specifically what our one-way ANOVA does, it's a parametric test. So in order for it to be utilized, the data from which we are collecting must be normally distributed. We can test that through our stem and leaf plots. And it compares the means of 3 or more groups. The groups are independent. They're not related to one another. Okay. The homogeneity of variance must be there. It assumes that. And the data to input and run the ANOVA has to be based on the means and standard deviation. From each group. So back to the original presentation on research designs, it's a little bit difficult to understand these statistical analyses and try to give you examples without going back to, well, why would you use an ANOVA? Well, you'd use an ANOVA if you have, for example, these types of research designs. So if you look at the design on the left, it's a little bit higher up. We have 3 groups. We have group 1, 2, 3. And we have 2 treatments. So we have treatment A, which could be, we could categorize that as maybe some type of behavioral intervention. And treatment B, it could be cognitive behavioral, so a combination of the 2 types of therapies. So you have 2 types, and then the 3rd group perhaps wouldn't receive any treatment. Now our post-test, which they classify as characteristic of interest, would be our dependent variable. And our dependent variable could, let's say, we're measuring the level of depression in each one of these groups. Okay, so going back, looking at our grouping variable is treatment A, treatment B, or control group. So it's parsed out into 3 different levels. Okay, so it breaks it down into 3 different groups, and our characteristic of interest, which is our dependent or outcome variable, they all receive the same depression scale inventory. So we'll monitor it. So based on the data collected from this design, you'll see we have 3 different groups, and we're going to look at the differences between each 3. So this type of design would necessitate the use of this one-way ANOVA. Okay? So let's say, for example, you have a design that's listed on the right. This is more of a non-experimental design based on observational data. So the design on the left is more experimental or quasi-experimental, depending if you do random assignment to each group. Okay? And you can manipulate the variables through different types of design controls, but on the right, you can't really manipulate any of the variables other than using some type of statistical controls. So for example, this design on the right, we can look at our earlier example of birth weight. So our criterion variable is also the same as our outcome. We could be looking at birth weight, okay, and our predictor can be ethnicity. So we have Caucasian, Hispanic, and African American in groups 1, 2, and 3. So that's our grouping variables, and what we did is we used a statistical control, and we're able to break out the different types of ethnic groups using some type of statistical procedure that identifies them as either 1, 2, or 3 into the system. And we enter it, and then they're artificially separated statistically and then analyzed, and we look at the between group differences. Okay, so this kind of helps bring it back into perspective when you actually see a design here and understand what type of design would necessitate the use of a ANOVA, for example. Okay, so back to our specific types of analyses. Kruskal-Wallis, again, you would use this specific type of analysis on one or both of the type of designs, assuming that if you looked at the variables and ran your preliminary analysis and realized that the data were not normally distributed, then it would necessitate this type of analysis. If, again, the data were normally distributed, then you use your parametric procedure, which in this case would be the ANOVA. Okay. The rest of the assumptions are the same. It's 3 or more independent groups. The dependent variable would be at least ordinal. So what would happen is depression or birth weight isn't necessarily ordinal, but it would be transformed into ordinal data and then run. And it looks at reports of medians, interquartile range, and so on and so forth. Here's a true and false, might be a little bit tough. The Kruskal-Wallis H test can be used with paired data. And like if you remember from the previous, it all has to be independent. Therefore, you can't pair it. Paired is another way of saying dependent. So it has fewer assumptions in the ANOVA, but the groups still have to be independent from one another or not related. So we say, we ask the question, how's the analysis of variance works? We have 2 different analyses within. We have the within and the between. So the within variance is a variance, are looking at the differences between, within each group. So let's say we go back to our example where we have treatment A, treatment B, and the control group, okay? And then we look at the outcomes for treatment A, and then the analysis looks at the within differences but within just treatment A, okay? But the crux of the analysis lie on this between subject variance. So we're looking at the differences between each group, okay? That's the most important part, okay? And it really helps to look at it when we have our distribution with our data and our means. So in this case, we have the mean of group 1 on your left, the mean of group 2, and the mean of group 3. And we're looking at the variation. You see the dotted line between each bell-shaped curve. this data is really normally distributed. You probably never really see data that clean, but for illustrative purposes, it's laid out this way. So we have the dotted line. So the analysis is really looking at did these results, did this data come out this way? Did they happen by chance or due to error? And that's what the analysis is really going to tell us. Okay, so as you can see, none of the data overlapped. Again, it was really nice. Oftentimes data between groups that are somewhat related, even though they're quote-unquote independent of each other, there's going to always be some level of overlap. But really, when you're looking at the mean differences, it has to be substantial enough in order to find some type of statistical significance. And therefore, that's essentially what the Anova is going to do for us. Here's another example where data is extremely overlapped, and if you can see the differences between means 1, 2, and 3, or groups 1, 2, and 3, are really not so different. Okay, so what you would expect to find when you have data this closely related, that the differences probably did more or less happen by chance, and if you ran the data again, the mean for group 2 would probably look a lot like group 1 and vice versa. So when the distances are smaller and the means are much closer, you're not going to find statistical significance. So in other words, the differences did happen by chance. When you actually conduct your assignment, you'll get a chance to create an Anova table via the data output from SPSS. It looks a lot like this. And here are the mathematical formulas. Really, we're looking at the between group differences, and we're really looking at, if you look over to the right, your F ratio and your p-value. The p-value being important and basically telling you whether the results happen by chance or not. Okay, but here's the important part here, and this has to do with post-hoc tests. The analysis of variance is going to tell us whether the results happen by chance or not between the 3 groups. And it could be 4 or 5 or 6 or more, but just staying with our example of 3. It doesn't tell us if 1 is different from 3 or if 2 is different from 1. It just tells us that the results didn't happen by chance. The post hoc will come in, okay, after the fact and do another set of analysis and look at the groups individually as in pairs, okay, to determine, was it group 1 and 2 that were different, or was it groups 1 and 3 that were different from one another? And then won't look at it as a whole. A lot of statisticians over the years have come up with various types of post hoc tests, stuck their names to them. Some are more popular than others. SPSS handles some of them. Some of them have to be hand calculated or used in a program outside of SPSS. The most common is the Chaffee test, the 2-key, most often used with different versions, but in this case, right here, the Chaffee test will give you that post hoc comparison, and you can select that as an option when you run your analysis in SPSS. So quickly, let's run through an example of running this analysis variance. Okay, so the research question here tells you right away that we're not doing any kind of experimental or quasi-experimental design. We're just looking at observational data. Okay, so it's completely non-experimental. And if you recall, non-experimental, it's difficult to infer causation from non-experimental data. It's really going to just give us some type of correlational information related to our outcomes. So do people with private insurance visit their physicians more frequently than people with no insurance or other types of insurance. So essentially we're looking at our outcome variable, okay, which would be visits to physicians, all right, so that's our outcome. And then we're going to parse them out through our grouping variable by looking at different types of insurance. So in this example, we use data from 108 adults, okay, to answer this question. All right, so here we have 4 grouping variables, which means that we're going to have 4 different groups, okay? Those individuals who have no insurance, individuals who have Medicare, TRICARE, and private, okay? So that's our grouping variable. And then our characteristic of interest, don't necessarily like that term, but that's the term we use in the book. Our outcome really would be the number of visits to their doctor, okay? So we always go back to our null. So we're running the analysis to accept or reject the null hypothesis. That's ultimately the objective here. So none of the groups will differ on the mean number of visits. So we're basically saying all the groups are the same. Okay. So our alternative, non-directional, at least one of the groups will have a different mean number. So we're not saying they will all be different, but at least one will be different from the rest. Okay. And again, the ANOVA only will tell us if the results didn't happen by chance. The mean differences. The post hoc will tell us specifically which group. Okay. So we're going to define our alpha level, which the most common will be at 0.05. All right, and our critical value again is always calculated inherently within the program if you use SPSS, so you don't actually have to define it or use the F value. Or the critical value table, which is located in the back of your book. So we'll move forward. We'll look at our assumptions. So we're going to assume a couple things, and this is up to the researcher in the initial aspects of collecting the data. Does the data collected constitute an independent random sample? That's done through sampling procedures. The factor, okay, which is also our grouping variable, okay. Type of insurance has at least 3 levels, and in this case it has 4, okay. The dependent variable, also known as our outcome variable, our characteristic of interest. See how confusing this can get. They just use multiple different types of terms. I think these authors do it this way to confuse you on purpose, but that's a whole other story. The dependent variable is our number of visits. It's our outcome, okay? And we assume that the data, when we do the preliminary analysis, that it is normally distributed. The assumptions of homogeneity of variance is not violated, okay? And that's done with the Levine's test and SPSS. And if the data were not normally distributed, of course, then we would move to the Gruszka-Wallis H test. So in this case, we can see that it's normally distributed. Okay, so if we look at it, those who received 2, there were 0, just 2, 10, 18, 20 number of visits. For 3, there were 20 number of visits. 4, there were 21. 5, 17, number of visits 11, 6, 7, 8, and as the number of visits got higher, the number got lower, so on and so forth. So if we just look at our descriptive stats, kind of starts giving us an idea of what the data distribution looks like a little bit better. So the mean number of visits for individuals who had no insurance was only 2.5 times. Those with private insurance, almost 4.5. Those with Medicare, 4. TRICARE, 4. Standard deviations around 1 to 2 for each. So it looks like there's not a lot of difference here based on the type of insurance. So it'll be interesting, to see what our data show, and it does show that the results did not happen by chance, therefore there's statistical significance. Okay, if you look at your p-value for the between groups, it's less than 0.05. So the write-up might look a little bit like this, and I always like to modify this write-up, but I'll read it here. Type of insurance is significantly associated with the number of outpatient visits made in a year. Okay, so in other words, based on these findings, that the differences between 4.4, 4.19, 4.8, 2.5 didn't happen by chance. So there is statistical significance. The post hoc test did reveal, which we didn't show the results from that individuals who had no insurance visited only at 2.5 visits. So really the difference lie with the no insurance group, and then the 3 other groups were pretty closely related. So the differences between the 3 other groups were not statistically significant, but when looking at the individuals with no insurance, there was statistical significance. Okay, so how can we tell which means are different in ANOVA? We look at the alpha, F ratio, post hoc, or p-value associated with the F-test. And of course, we can tell the mean differences between each is with the post hoc, because again, the general analysis of variance equation will only look at did the results overall between the groups happen by chance or not. It won't tell us the combination of which groups, and the post hoc actually tells us that. This concludes the presentation for Chapter 7.